So we can now move to the second presentation. So let me introduce Jean-François Sauvage from LAM. So the LAM is the Astrophysics Laboratory in Marseille. Jean-François graduated from École Supérieure d'Optique, so it's the same school than Karine Mathieu. He holds a master's degree in astrophysics and instrumentation. And then in 2007, he earned a PhD where he studied exoplanet imaging with an instrument called SPEAR. And he started to work at ONERA in 2007 as an engineer. So ONERA is a French research center in aerospace, I think. And now he works on adaptive optics for astrophysics. And more recently, he focused on active optics for space observation with the LAM in Marseille and with ONERA. Okay, so I think everybody's seeing Jean-François's screen now, so you can start.
Okay, can you hear me?
Yes, I can hear.
Yes, okay. Thank you, Marin, for the introduction. So I wanted to thank you for this opportunity to present this joint team between LAM and ONERA developing instrumental research. So our field of application is started with adaptive optics observation from the ground. So for astrophysical telescopes from the ground, we care a lot about atmospheric turbulence that somebody was asking this question about just previously. And then we extended our field of research into space optics, where active optics in space is required when the instrument is suffering from thermal deformation and the optics are evolving. So just a bit of detail on this joint team. It's between LAM in Marseille, so very close by Fresnel, and ONERA, so the French Aerospace Lab that's situated in Paris. So myself, I'm employed by ONERA, and we developed this partnership with LAM, where since 5 years now, I'm working at LAM, but still with ONERA employment. So there is this team working on instrumental research and development, so where we are close to 20 people now, and with PhD students, postdocs, and engineers and researchers working in this field. So talking about space optics, of course, space optics is providing images taken from space. So it corresponds to a very challenging trade-off. It gives application to many different fields. Of course, for astronomy, when the satellite like Hubble is looking at the sky, but also for climate observation, when the satellite is looking to the Earth, defense and security, and a lot of different fields. In all these fields, the scientists, people, and guys looking for applications are engaged in a race to increasing the optical aperture. Behind this is the key parameter that Karine introduced just before. A larger optical aperture gives you a smaller diffraction size, and then you have a better resolution. In parallel, increasing the optical aperture increases the number of photons you get and the SNR. Another key parameter which is important for space is also the revisit rate. Concerning the Earth observation, if you have a very high resolution image of one spot in Earth, you also are interested to see this spot as often as possible. Having a revisit rate, an important revisit rate, requires most of the time to have multiple satellites and constellation of satellites that will pass by one after another, looking at the same spot on Earth, giving you the temporal evolution of an area on Earth. So today, having, but maybe Karine can contradict myself, but several times a day revisit rate is not available today in space observation. On the other hand, the space optics are very constrained. First, you know that you have to pay a lot for every kilogram you want to send in space. We are also limited in terms of size because it's related to weight, and also because of the limited space of the launchers that you can use to go to space, and in cost. So this is the reason why we see appearing this term of new space, that is low-cost access to space, and we see appearing small platforms like CubeSat and NanoSat, which are standardized, very small-sized satellites that reduce the weight, hence reducing the cost, and allowing, which is a very good point. Sorry, now I have an animation that should appear. Okay. So this apparition of new small platforms and low-cost platform is very compatible with increasing the revisit rate, because they are low cost, so you can buy several of them for the same price and having high revisit rate. But you see appearing here a very big contradiction, which is if you have a small platform, then you cannot have a large optical aperture fitting inside a small platform. So this is the contradiction we are trying to work on in this team, to address this paradigm and to provide some large apertures, large optical apertures in a reduced volume or for a reduced weight. So to address this, there are two solutions to this problem. The first one is to use monolithic optics, but to try to provide lightweight monolithic optics, so working on materials and the way to industrialize these optics. The second way is to use deployable structures in space. Instead of sending monolithic optics, you divide the telescope into several pieces, into segments, you fold them inside the telescope, and you open them when in space. So one of the first satellites that will use that will be the James Webb Space Telescope from the US, that hopefully will be launched into 1 or 2 years. That will create a very large aperture in space, but we are far from the paradigm we want to address. The James Webb is 6 meters wide and costs $10 billion, if not more. So these two solutions are introducing a new challenge for space, which is to maintain the optical quality. If you want to have a good optical imager from space, you need to have very low optical aberration. You need the wavefront to be as flat as possible. Having lightweight optics helps for the weight of the optic, but introduce a more high sensitivity to the thermal deformation of the optic, so reducing the quality of the optic. For the second solution, deployable structures in space, of course, points out the fact that the three independent pieces that you hope are forming a very good primary mirror, they are subject also to move one with respect to another, also due to the mechanical deformation of the main structure. So this points the need for active optics, which is the real-time compensation of the optical deformation of the instrument. Okay? Which active optics means on board the satellite, you need to be able to measure the wavefront aberration and to correct for it in real time being at least as fast as its default. So this is just the introduction for my talk. I want to give you quick highlights on two projects that are components for space optics. The first one is MADRAS. So in LAM, we have developed a deformable mirror for space active optics. And we also have developed some techniques to provide particular shape for optics, which are off-axis parabola, for monolithic optics, with very high quality. And I will detail more a future project that we are preparing now, which is Asimov, which is a project of a deployable telescope on board the CubeSat. So I begin with these two component aspects developed at LAM. So as I said, sorry, I hope you don't see this window from WebEx. So Tango was a proposition of a demonstrator of TAS to show that we can build a primary mirror, a very large one, 1.5 meter, with a lightweight capacity, and that we are able to compensate for its deformation with an active optic system composed of a wavefront sensor and a beam corrector situated upstream the telescope. And what LAM has been working on was to develop, so this particular component of the deformable mirror here, dedicated for this application. So it was a research activity at LAM, which with two PhD students working successively on that aspect. There has been a prototype built and tested between LAM and TAS and integrated to a flight model at TAS. So the complete system didn't fly at the end, but was up to a very high TRL level, very close to being ready to fly. The very important aspect of the development here of this component is that the goal was to develop this deformable mirror with a capacity to have degrees of freedom, deformation, that will exactly fit the expected deformation of the primary mirror here. The primary mirror here was expecting deformation following a few numbers of Zernike polynomials, and this deformable mirror was designed to have exactly the shape of deformation able to compensate for it. So this is why you see this particular azimuthal geometry of actuators here that are pulling on arms that are linked to this to the central optical reflective mirror here, and was able to compensate for the aberration, the wanted aberration. In a set and forget case. So this is also an important point. In space, you want to have the lowest consumption possible. So being able to put an actuator in one position and then you stop, you can switch it off and it keeps its position was an important aspect. So, okay, at LAM, we developed this demonstrator of deformable mirror. On another aspect, LAM has developed also a way to produce very high quality space optics. So here we are a bit less talking about the large apertures of our active optics. It is in the context of the WFIRST instrument. So it's WFIRST is a telescope, a US telescope. That will, one of the instruments will be dedicated to the direct imaging of exoplanets. So this is an astrophysics application that requires a very, very high quality of the optics at a nanometer level for the wavefront shape, and for the rugosity has to be 1/10 of a nanometer, typically. So all the optics of the optical path has to be very high quality. And LAM developed a stress mirror polishing method to minimize all the residual of the optics polishing, even when producing some strange shape optics. So here in this case, the idea was to produce off-axis parabola. So the shape is not of circular revolution. It corresponds to the side of a parabol. And it should be composed, the shape of the optic should be composed of astigmatism and coma. So the idea of LAM is to develop some very dedicated shape mirror here that can be lightweight mirror, to apply on this mirror that is perfectly flat, to apply on this mirror a constraint with a 4-point constraint like this, but it can be adapted to the kind of shape you want. So the mirror on constraint is polished with a spherical shape. At the end of the polishing process, and this polishing process spherical can be of very high quality, you release the constraint, and the elasticity of the material gives exactly the shape that you wanted. So, of course, this is closer to mechanical finite element analysis research, but it's a very good techniques that at the end will give you exactly the shape that you want. So this is some pictures of the flight model that has been delivered to WFIRST team, to NASA. And that shows the system after polishing. So of course the deformation is very, very small, but you see that here the interferometer shows some very nice fringes pattern here. The residual wavefront error was estimated to 1.5 nanometer. And the rugosity, or roughness, sorry, was 0.2 nanometer, 2 angstrom. So that was for the two first aspects, the two components for space optics or active optics, space active optics. I want to go now to a third space. I will go a little bit more into the detail of this project. This is a future project, Asimov, that we are proposing to Europe. The goal of Asimov is, so the acronym stands for Automatization of Movable Optics for High Angular Resolution Earth Observation. The idea is how to increase the aperture of a satellite, of a CubeSat. So the context, of course, as I said, is the new space. We want to address low cost and small platform to a high revisit rate. So this low cost platform is very good for the revisit rate because they are low cost. but they are not very interesting for spatial resolution, because even with an optic aperture limited to 10 centimeters, the ground resolution will be 3 meters, 2 meters if you can have a very low low orbit, and you can go with a small wavelengths. But so the objective of the project Asimov is to demonstrate that we can have large aperture even on small platform in space by deploying a telescope. So it means the primary mirror, the secondary mirror, and the baffle, which is protecting from the parasite light. The goal is to reach 30 centimeters once deployed. This would provide a metric resolution on the ground, so 0.7 meter resolution depending on the orbit, the wavelengths. So this is the resolution of Pléiades actually, so which is not that bad. The idea is, of course, deploying mechanically the primary and the secondary mirror will turn into residual aberrations that will limit the quality of the optics. So we need on board to have active optics, able to measure and to compensate for all possible alignment errors. And we also want this satellite to be as autonomous as possible. So we will develop an artificial intelligence to help to co-phase all these segments and provide the best imaging quality. On top of the objective of Asimov, there is to establish a scientific roadmap. We want to work with scientist teams to demonstrate that this telescope is really useful for as many people as we can. So that was one of the first work that we developed in this project, was to gather a science team around this concept. So we found a number of domains, very different domains, in which having high angular resolution coupled to high revisit rate would be very interesting. So climatology is one. I won't go into detailing all of these points, but measuring the Earth's albedo in very heterogeneous scenes and urban scenes is a physical quantity that is today not available from space observation. It's not available, and it's extremely important for all the models of the climate observation. We are lacking information on small spatial scale and with as often revisit rate as possible. So detecting also carbon aerosol source is an important application. We are thinking also on a natural disaster, so monitoring of flooding, forest fires. You can have a monitoring of a flooding day after day or during the day of different areas with a good resolution, so that you can in real time give information to the rescue people on Earth on the surface to help them with security of people. Of course, defense application, having a metric resolution for defense is a key resolution. It helps to detect and identify vehicles. And if you count the vehicles, you can count the people. So that's a very important application. I'm not going through all of them. Astronomy, for solar system exploration, there is a lot of phenomenon, of transient phenomenon that would benefit from having high resolution and high revisit rate. We are thinking about the volcanism on Io, the plumes of Europe, the geysers of Encelade, a lot of applications that would benefit from this. So we gathered a science team with different laboratories here that are embedded in the project to provide us with this kind of requirements. What do you need exactly at the end? So there is LATMOS, atmospheric laboratory in Paris, ONERA in RAE, in Avignon, the Space Army, French Space Army, LAM, and we are also beginning discussion with CNES to see how to involve CNES in this project. So now I'm entering into the details of the optical quality of the system. We want at the end to reach diffraction limit of this small aperture, 30 centimeter aperture. What does it mean? If we deploy the telescope, the primary mirror, and we rely only on the mechanical precision of the deployment, we end up with something that will be, I say here, 2 microns positioning. This is a bit optimistic, maybe more 5 microns positioning. This is what we can hope the best. You see here that this image of the viewport of Marseille is clearly not at the good resolution at the end. We are not able to count the boats or to distinguish them. Phasing with a sub-lambda precision in the visible, you can reach lambda over 3, lambda over 4 precision here. you end up with a correct global image, but if you look at the detail, you see that still you are missing the final resolution of the image. You really need to reach something close to a few tens of nanometers to have the final resolution and have the best imaging capacity. So this is the numbers we have in mind. It's a bit aggressive number. We know it's difficult to reach it, but that's why we want to develop this project, to show that we can reach also very high optical quality in space. Yes, okay. So how to reach, what are the strategy to correct for these errors? We are not going to put a deformable mirror inside this project, because the CubeSat is a very small space and we want to keep it as simple as possible and also as light as possible. So we will directly add some actuators to move the segments themselves. And the idea will be once it's spaced, we have two strategies to face the segments. The first one is the brute force method. We know that by looking at a star, so it means you point the telescope towards space, and looking at a star, there are a lot of methods that allow to co-phase the segment just by looking to this image here. We'll give details a bit later. Then you turn back the satellite toward the Earth, and you can make your observation. Of course, this is brute force, so a lot of algorithms exist, but it's not very accurate, because between the moment where you have co-phased the segments and the moment you point toward the Earth, turning back a satellite on 180 degrees is an operation that can take a lot of time, and the orientation of the sun will not be exactly the same, the deformation of the satellite won't be the same, so the phasing will not be perfect. So during this project, we will work on that aspect here. These are some algorithms that exist today, so this is why we consider the solution in the first aspect. Algorithms are among elastic. I will give some detail on that. Phase diversity, image sharpening, that are methods that are allowed to make this phasing here. The goal being that when you deploy the segments, if the segments are completely misaligned, you will end up on your detector with 4 images of the stars, and you just want to superpose them as fine as possible until you have a diffracted spot here. Maybe you need only one algorithm will be able to do it, or you mean a combination of several algorithms that's still to be studied. So this is a demonstration of this elastic algorithm that's developed at ONERA, showing here in a numerical simulation on the left part with the geometry of this CubeSat with 4 segments here. So this algorithm requires 2 images, one, let's say, normal images, and 1 images with an additional diversity in the segments. And from the processing of these 2 images, you can retrieve the position of the segment. And we also made some demonstration with a kind of different shape of pupil here, but still in the same, let's say, the same domain, showing that we are able to co-phase the segment. So the second strategy, which is more risky but more interesting, is to develop an onboard artificial intelligence. We call that the SMART method. The goal would be to remove the calibration step where you observe a star and you point toward the Earth directly. And the goal would be directly by looking at the Earth scene that's passing by very quickly under the satellite, just taking an image to be able to retrieve the position of the segment and to phase them. We would gain a lot of time here. So that would be very, very interesting. So the idea would be to develop neuronal network algorithms with a learning phase on the ground here, where you train your artificial intelligence with known high-resolution scenes from the Earth in different situations, and you train your satellite or your artificial intelligence to estimate the phasing and to correct for it. So this is a central part in Asimov. This is a research part of Asimov where we want to work a lot on that. There will be a space for PhDs and postdocs on this aspect. Last information, so we are not starting from nothing in this project. We are working with a Scottish laboratory that's called the ATC, Astronomy Technology Center, that developed since the last 4 years a prototype named High-Res for high resolution, where you see in this nice movie here the shape of a CubeSat here, so 10 centimeter side, with the 4 parts of the satellite opening with optical quality here. So today they are reaching a 5-micron precision of mechanical deployment. And now, okay, this is not making a telescope. This is only the primary mirror. So there is a lot of work now on the secondary mirror deployment and the baffle deployment as well. So as a conclusion, I showed you the activities of this LAM-ONERA joint team and collaboration. So we are doing research and innovation in optics. We are developing some innovative components and also providing space qualification in some complex situation. So we are working in optical and infrared imaging, centered on the high angular resolution aspect. Developing as well waveform sensing and control, optics component, and developing a system approach also, not only at component level. And finally, we are hiring. So we have we are opening positions in postdoctoral position, engineer position. So don't hesitate to contact me for more information or Mark Ferrari, and we will give you some hints on that. That's all for me. Thank you for your attention.
Okay, thank you. Thank you for this very interesting talk. There are some questions. So Pre2 asked why we can't use an array of CubeSats or nanosats to build like an interferometer telescope, as we have some on the Earth.
Very interesting questions. So you have to realize that building an interferometer in space is something with CubeSat is something that is, in terms of engineering, in terms of instrumental research, is something that is 10 times more complicated than doing this project. This project here, everything is mechanically combined. Okay, we just move open optics. This is a simple operation. We just align them. This is a simple operation as well. And at the end, we provide high-resolution image. Having an interferometer is one step more complicated. We can think about sending 2 independent CubeSats that will assemble in space. We call that the docking, or having free-flying CubeSats observing the same target and recombining optically their light. But it's also steps that are much more complicated than doing this. You need to control the wavefront in a more complex environment, let's say. So Asimov is actually a first step that will demonstrate that we are able to do active control, active optics in space, autonomous active optics in space. Once we are doing that, then we will go to free-flying satellite, docking in space, and so on. That's the logical development.
Okay, thanks. So the next question is from Camille. Camille asks if CubeSats could be useful to far solar system exploration, or if this kind of satellite instrument is not powerful enough to go so far.
Okay, so I guess the question relates to the data transfer between the satellite and the ground and the Earth. Of course, when the satellite is in low orbit, it's easy to communicate with it. Well, easy, maybe not so easy, but when it's around Pluton or Charon, it's super far away, and then a CubeSat will not have enough power to send the data to Earth. It requires a large radio antenna and a lot of power to send it. The idea for solar system exploration is more to have CubeSat as an auxiliary telescope. So you launch a big telescope around Mars, like the big one that have been sent recently. And once it's in orbit around Mars, it sends satellites. And the satellite it sends a CubeSat. And the CubeSat then sends back data to this satellite, and the satellite sends back data to Earth. That would be the way to do it. That's a very important aspect, of course.
Okay. So question from Imran. Imran asks, what kind of aberration causes you take into account and at what rate your adaptive optics system can correct those aberrations, if the aberrations are dynamic in time?
Okay, so good question. There is a kind of semantic distinction between an adaptive optics system. Adaptive optics is more for the ground system that corrects for a perturbation that comes outside of the system, so atmospheric turbulence. And active optics is more to correct the observing system itself. Okay, so here, what are the aberrations we are talking about? It's more thermomechanical deformation due to different orientation with respect to the sun. You know that in space you have a very large temperature gradient between one side and the other of the satellite. You can have several tens, if not hundreds of degrees difference between two sides. It makes the optics at an optical level, let's say a nanometric level, the satellite is deforming. So first, it's due to this is the cause of the aberration. It's dynamic because when you are doing orbit, low Earth orbit, your orientation with respect to the sun is constantly evolving. Okay, and at which frame rate? Well, it depends on how fast is your orbit, but typically 300, 400 kilometers, it's 1 hour and a half orbit. So typically, the kind of reaction time that we want for active optics in space is linked to that 1 hour and a half. You want to be faster than this. How faster, I don't know exactly, but I guess within a few minutes, that would be something reasonable, I would say.
Great. And then the last question, I think we have a question from Luis. So he's talking about the mirrors, the mirrors that you showed. That's having this form in the first mirror, the sort of periodic in Cartesian coordinates. So does it affect the transformation function since the symmetry is broken?
Okay, so sorry, tell me a bit more on this question. What slide are you referring to?
So I think it's the slide before.
It's in the Asimov project, or it was in the first project?
I think it's no. Okay, Luis, if you want to ask.
Okay, Asimov. So I think I see what you're referring to. I think you are talking about this one here, right?
Yes. If I'm allowed, just to precise, so the idea is that since your primary mirror is now has this like rectangular shape.
Yes.
The MTF, I would imagine that would depend on the direction. For example, in X and Y direction, you would have a higher special frequencies entering the system. But if you go to 45 degrees or this type of thing, then I think information would be missing, and this somehow would affect the MTF. But maybe I'm being too naive, and this doesn't happen.
No. This is a very precise question, and actually you're right. So here, this is the difference between having a diffraction limited instrument and having not diffraction limited. Here, this is the shape of my primary mirror. Okay, so 4 different segments here. You can see in the second image where each of the segments has been voluntary, on purpose, they have been tilted. Okay, so what you see in the corresponding image is that you have 4 spots, each spot coming from one of the segments. And you see that each of these spots here has a geometry that is not circular. It's a little bit elongated. Okay, it's elongated in the direction of the smallest part of each of the segments here. So when the segments are not aligned, like it's the case in the beginning of the animation here, where all the spots are in this area, each spot has this kind of shape. But when you manage to superpose all the spots at a very high precision, then you end up with a diffraction PSF. Let me show you. Then you end up with a PSF that looks something like this. This is the PSF of the perfectly phased segments of Asimov here. So, of course, there is this square geometry that appears, and there is 4 lobes here instead of having one circular ring. But still, I think the NTF is a bit perturbed by this aperture here, but not that much.